And let's continue with the second section of Lecture 2. So we are in the high-dimensional feature spaces, and we want to now explore why those specific representations have specific challenges. Why should we care about high-dimensional data? And we begin with a, I'm sure, truly motivating example for you guys. We play a baby shape game. Yeah? So if you have a baby, then maybe you can play this game with your baby. So here you have a set of items, and you ask the baby to group these items. And you see, so this set of item and this set of item, they're basically the same, but depending on what the concept, what the context is, you may group them in in different groups. Yeah. So here is a grouping based obviously on the shape of the items. So here are the rectangular shapes. Here are the more spherical shapes. While here you consider not the shape of the items, but you consider the color of the items, and then you end up in a completely different grouping than here on the left hand side. So here are the green, here are the green items, and here are the orange items. Yeah. So and if you have, consider an example where you have features. So your objects here, the items are represented by features. Say 10 features, 5 of the features represent shape features, and the other 5 features represent color features. So what is the correct grouping for this data set? Yeah. So the lesson to learn is, in this data set, I just told you, with the 10 features, 5 represent shape, 5 represent grouping. There are 2 different semantic concepts hidden in this data. So 5 features for the semantic concept of shape, 5 features for the semantic concept of color. And that may be the case in any raw data, and of course the corresponding patterns can only be found if you focus on the right set of features. So if you focus on the 5 features representing shape, you probably end up in the left-hand grouping. If you consider or focus only on the 5 features representing color, you end up in the right-hand side. Yeah. But the question, of course, here is, and not only here, the general question is how to really determine the correct subsets of features that are responsible or represent a specific semantic concept. Typically you don't know that, especially in unsupervised case. But anyway, that should give you a first example that high-dimensional cases, if the number of features grows, there may be much more semantic concepts than just 1 or 2 in the data. So that is the really ugly thing here in that case. So why is that an issue? I just somehow mentioned it a little bit. So going back in the good old days of data mining, well, some 10 years ago or so, nobody can imagine anymore, but some 10 years ago or so, data generation and also to some extent data storage was really costly. Yeah, as I said, hard to imagine, but those were the days back then. So people were very carefully when generating their data. So domain experts typically consider very carefully which kind of features, which kind of variables should be measured, how to design the experiments to measure exactly those things, how to design a feature transformation from raw data and stuff like that. Yeah, so those were the days. And the consequence was that the data sets we get as the data miners, as the machine learners, as the data scientists were very well designed and potentially contained only a small number of the relevant features. Yeah, so as I said, those were the good old days, because we typically didn't have the problems of high-dimensional feature spaces, or even if the feature spaces were high-dimensional, we were pretty sure that most of the features were really relevant for one specific semantic concept. But things changed, obviously. Well, we as data scientists, we also are a little guilty for that, because we told those guys, well, we can do anything, we can do it, just measure everything, yeah. And with the big data era, things changed a lot. So generating and storing data is easy and cheap. So people tend to measure everything what they can, even something which they don't think that they can, yeah. So that also includes, of course, even more complex feature transformations. Consider your smartphone, your cell phone. It produces a lot of data without that you know that it does. Yeah, I mean, probably you know that it does, but you don't exactly know what specific data is produced, and that's all for free, more or less. Well, and nothing is for free, of course. You pay with your data, but not with your money in that case. But anyway, yeah. So generating, storing data is extremely easy, extremely cheap, and the data science mantra, as I told you before, was okay. We can do that. We can analyze all that shit, all that big data. So just integrate everything from everywhere. Technically, it's possible. So yeah, just go ahead and record anything you can. And the consequence now is that the data sets are not only high dimensional, but also contain a large number of features where the relevancy of each feature for the analysis goal is not too clear. So for example, going back to our baby shape game, so if my application is on grouping the things for shape, but I still have my 10-dimensional feature space, including the features for shape and the features for color, that's actually what very often the situation is. Yeah, so I have a particular application or a particular goal for the analysis in mind, but I still have a very, very high-dimensional feature space, a very complex data set, just because I didn't care too much about data generation. I just generated and grasped anything what I can get, so to say. Yeah, and that's what we face nowadays. That we have a lot of data sets that are high dimensional, and as I said, containing a large number of features, and we don't know exactly if all those features are really relevant for what we want to do, or if they are just irrelevant. So yeah, just that you know, some examples here. High dimensional data is not a myth. Yeah, it's really existing. So for example, for image data, you typically end up in, if you don't do deep learning nowadays, you extract some low-level image descriptors, for example, like color histograms, textures, shape information, stuff like that. They can be they can result in, say, 100-dimensional feature spaces. Yeah. And then if you go for higher level features, image features like regional descriptors, you end up in feature spaces that are between 16 and 1000 dimensional. Yeah? And then you have these really high level features like SIFT or stuff like that, where you extract sets of features. Yeah? So many features, many samples of features, and you end up in really thousands of features for images. Yeah? So here people are really interested in problems with high-dimensional feature spaces. Another example we actually worked with 10 or 20 years ago is data from a medicine application, metabolome data. So the features are the concentration of one specific metabolite in the body or in the blood of a patient, intermediates or results of metabolisms. And we worked for the Bavarian newborn screening here. So in Bavaria, I think it's still active for each baby. They take the blood and then they measure the blood concentrations of 43 of those metabolites within the first 48 hours after birth. And from those concentrations, they want to really defer or derive patterns for metabolic diseases. Yeah? And what you end up in this data set here is something which is, or a data set which has something between 50 and even 2,000 features in those medical domains. Yeah, so a lot of features, and of course the doctors somehow have some hypothesis why they take those 43 metabolites in that case, for example. But we found out that not all of those metabolites are exactly responsible for a given metabolic disease. Yeah? So some are responsible for disease 1A, so to say, and another subset of the metabolites are responsible for metabolite B. So very similar to the baby shape game, actually. And the third and the fourth example here, so again, biological domain, microarray data, which is probably not the application you work on nowadays as bioinformatician, but anyway, I did that in my PhD a little bit. So the features actually, so depending on how you analyze this kind of data, features correspond to genes, and you can measure up to 20,000 genes simultaneously, so you end up in a 20,000 dimensional feature space. Yeah? And very often in that case the dimensionality is much higher than sample size, and we will come to the point later what that means to us. Yeah? And finally, very often you work with text data. Still, the way you work with it is to extract features like term frequency features. So in that case, term frequencies represent the frequencies of words or terms in a document, and depending on the vocabulary you use, so typically you're strict then the words you count to a fixed vocabulary, and depending on that size, you end up in 5,000 to 20,000 features, or even more, yeah, depending on the whole thing. Yeah, and often in social media and Twitter and stuff like that, you have to work with abbreviations, colloquial language, special words and stuff like that. So this even pumps up your feature space, because this pumps up the vocabulary you're working with. Yeah. So all those examples should show you that we really have to take care about high-dimensional data. And the question is, why should we really care? Well, there are a lot of problems with high-dimensional data. The so-called curse of dimensionality, you probably heard of it before, and we want to try to explore this curse. What are the problems associated with these high-dimensional data? And here is a short overview. We will tackle some, not all, of the problems, but those problems are probably the most important things for us in the data mining area. So we will see that distance grows. Well, sounds like trivial, but what is the consequence? The consequence is that the contrast of distances diminish. So the so-called concentration problem is that follows from the distances that grow. Another consequence is that the meaning of the neighborhood concept will be deprecated. Neighborhood concept will be meaningless. Another thing is that the data space grows, which means that the hypothesis space grows. We will have a lot of empty spaces, and that has some impact on tail distributions. And then going back to the baby game, we will have different semantic layers, semantic concepts in our data set. But now we will have a closer look on all those problems, but just that you know, there are a lot of other problems which are probably not that relevant to us for data mining, but may have an impact to other domains like, I don't know, computational geometry, for example, or stuff like that. Yeah, just that you know. And now let's have a closer look on those problems. So we begin with the distances that grow.